So today we're going to talk about worst case climate change. What is worst case climate change? How quickly could it occur? And in fact, what can we do right now? And that's really the crux of what we're going to get to. Now look, this is controversial, and it's meant to be controversial. It is really meant to make you think and research and act and really give some consideration to some of the real data that is now out there. We will consider the worst case. Now, this worst case would suggest that the IPCC models are too conservative. We will see if that's true. So we're going to present some data that's really meant to make you think. And look, I am not suggesting that this is going to happen, but I'm just encouraging everyone to learn more and act accordingly and act really smartly in the choices that we make that use energy and generate CO2. Let's assume that this thing can't be modeled and in fact discontinuities are the norm. You know, that gives us a bell curve of possible outcomes. Just for argument's sake, let's say the IPCC was very conservative on that bell curve because they had to get hundreds of scientists to sign off. So really what ended up getting published was the most conservative view, or a pretty conservative view. And let's for today talk about not a conservative view, the opposite side of that bell curve. And again, just for argument's sake. So the IPCC, most of these models were in fact assuming a straight line approximation of a certain way that ice melts and these sorts of things. But in fact, what we often see are discontinuities. And we see these discontinuities really throughout the environment. We've seen discontinuities throughout history and climate change. And I would say that we may see these discontinuities again. And in fact, discontinuities are quite common throughout nature. Just looking at water, right? It's either solid or liquid, and there's not too much happening in between. So you can see that there is a major discontinuity. And in fact, a lot of what we're talking about here when we talk about climate change has to do with water. So, of course, that's not a surprise. We're going to do a quick review of CO2 and temperature. I think everyone in the audience knows that as CO2 rises, temperature rises. We've seen this throughout history. You can see it in the charts here in the graphs. The rain patterns change, Europe could freeze, glaciers melt, and in fact the CO2 level in the atmosphere has been under 300 ppm for some 40,000 years. Today the CO2 is, in the atmosphere is nearing 400 ppm. So we really don't have any modern history where we see these numbers. In fact, as of today, I think it's at about 387 ppm. So we should note that it's never been that way. And the projected temperature rise, in fact, in the IPCC itself is, in fact, this. The best case is about 8 degrees Fahrenheit, and which would tie to the 550 ppm stabilized CO2. At 750 ppm, we're looking at really a good case that takes us to 12 degrees and sort of status quo. If we keep doing what we're doing, at some level, the upper bound, even in IPCC, takes us to some 14 to 15 degrees Fahrenheit with 1,000 ppm in the atmosphere. So this is right out of those charts, and this is not meant to scare anyone. It just is what it is. This is a great video of what's happening to the surface temperature over time, and you can see as the years progress, you see data in Celsius there, or centigrade, and you also see it in Fahrenheit across the bar. And as you see more of those red, as we see more of those red and sort of almost purplish, really dark red areas come up, you see that we start to approach some areas, certainly at the South Pole and absolutely already at the North Pole, that are approaching 15 degree Fahrenheit rises. So this can be tracked over time. It's very clear, and that takes us out towards the end of the century. But I don't think we want to be on an Earth that looks that red and that dark. I think that's a bad idea. This is a fact, and we should just know this. The North Atlantic flow is a conveyor that heats Europe. Many of you have heard about this before. Without it, Europe would naturally be under ice. In fact, it'd be quite a bit colder. But there's been quite a shutdown that did happen many, many years ago, 13,000 years ago and about 8,200 years ago. And when it shut down, it virtually shut down in about 10 years. It was very, very quick. And when we look at the NASA monitors since 1990, the north flow is already down 30%. So, and the undercurrent appears to be down about 50%. That tells us that this flow is indeed slowing down. This is not a surprise. These are facts. This is what the monitors show. And of course, this really isn't modeled in IPCC. I think that's generally difficult because we don't know where it's going to go. This is a really wonderful video that you can take a look at how these flows work. And in looking at this, you can see that you know, the warm water comes on the top, the cold water comes on the bottom. But then as the ice melts up north, it changes the salinity of the ocean. And what happens is that flow can shut down, just like you see in the video right here. So let's look back 8,200 years ago. We said that flow stopped. What happened? Well, Europe actually cooled by about 5 degrees, and glaciers moved all the way down through Europe. So they saw a huge change in surface temperature. We know this from the fossil records. We can see what happened. And so this did happen. This is a fact. It's not that it might happen. We don't know if that's going to happen again, but it did happen 8,200 years ago for other causes, and we should note that that's the case. Well, there's something else that really helps these flows occur, and these are these vortices in the North Atlantic, and they are very, very important because that is what swirls the water from the top surface all the way down to the bottom and keeps those currents going. They're somewhat called ocean chimneys in some circles, and these ocean chimneys are the source of the Northern Atlantic flow. They're quite large, 6 miles wide or so. In 1995, there were 24 documented major vortices up in the North Atlantic. By 2005, there were only 2 left, and in 2008, maybe there's only 1 left. No one's for sure because the funding ran out to go find these things, which was actually out of Europe. There's no models for this out of in the IPCC. The source for this is Dr. Peter Wadhams. You can look it up. Really, really good data. And in fact, over the last year or two, we've seen things like Athens, Greece look like this all of a sudden. It shouldn't snow in Athens like this, so that was February 2008, but we may in fact see more of these. So when we talk about climate change, we're not talking about the whole world getting warmer. We're talking about much of the world getting warmer, but some areas possibly getting colder because of these changes in flow and changes in cloud cover and changes in rain, everything else. Actual Arctic melt versus the IPCC models. Well, you can see here that black line is what we've actually seen on the satellites. And this is a little bit scary because the IPCC models basically suggest that we will see the Arctic melt by about 2100, very roughly, right? Completely gone, North Pole empty. But as many of you have read already over the last few years, we've seen an acceleration of that that do not match any of the models, even the most aggressive models from IPCC. And in fact, if you extrapolate this using the NASA satellite data that we have through 2007 so far, it says that for sure the North Pole will be melted if there's no further acceleration by 2017 or so. And there's quite a few people saying it'll be before 2010. So you could see the difference between the actual data that we're seeing and the more conservative models that we've put forth. And this is actually just a wonderful video of that actual occurrence. And this is through 2007, maybe more than that in subsequent years. But that's what happened to the North Pole. You'll see about half of that ice was gone by September. Well, let's talk about Greenland. Everyone talks about Greenland. Everyone, you hear a lot about Greenland. And yes, there's a lot of ice. But more than that, let's look at the actual melt per year, because there has been a net loss every year since about 1980 of ice melting in Greenland. So it's been melting. It's not that it's not melting. It's melting and it's accelerating. In fact, some 300 million acre-feet now on an annual basis as of net loss. And so if we look at that all piled up, by the way, if this all collapsed, the ocean would rise quite a bit. We don't want it to rise 23 feet, but if it all collapsed, it would rise 23 feet. But we're not talking about collapse. We're talking about continual melting right now. And the models don't consider anything like that. But let's look at how fast that's going, because we need to accumulate how much ice really has sort of left the scene. So the cumulative millions of acre-feet lost, as you can see, we're talking about, you know, north of 3 and heading to 4 billion acre-feet lost by 2010. This is absolutely substantial, and this is already going on in Greenland. So this isn't something new. And you know, if you were to look at that in terms of the United States, that's the equivalent of covering the U.S. With 1 foot of ice through that section, through this section, through the midsection, all the way to the east, and doing it again and making it 2 feet thick across the entire U.S. That is how much ice has melted off of Greenland since 1980. This is a serious problem. It's really happening. That's just a fact. It's not a model. That's a fact. Lubrication. If you don't know about this, we really didn't know about lubrication until about 2000. We thought the ice was really attached to the rock. But what's really happening in Greenland and other places is water is melting through the cracks. It's melting on the top of the ice. It's melting down through those cracks. It's lubricating the ice pack underneath, and now you've got subglacial lakes forming. The model, so you've got situations where a model says 10,000 years of life left in a certain glacier at the current melt rate, but the reality, it could be days or any day, because these things could just break away at any time and slide right off the land. And it's quite possible the models, of course, didn't consider that, and maybe we should have considered that. And you could see some of this observed flow here, for example, with the subglacial lakes, and you can see the ice actually flowing over those subglacial lakes. You know, this is the Larsen B ice shelf down in the Antarctic. This is another example of something that happened much quicker than we had any idea was going to happen. And really, in the period of just a few days, we went from a very, very large ice shelf to a bunch of little pieces floating in the ocean. Let's take a look at that more closely. That ice shelf in the Antarctica was some 12,000 years old, 100 square miles, and 650 feet thick. So think about what we're talking about. That little picture, you know, here on the video doesn't do it justice. The model said it would last some 10,000 years, but in fact, it broke up in 3 days in 2002. And it was a cork holding back an awful lot of land-based ice. And that cork is now, well, it's out of the bottle. So we're going to have to consider that and what that does to every model that we had for the Antarctic. Behind that is really Pine Island and Thwaites, and it's been the same for decades. It's now losing 70 million acre-feet a year starting in 1995, and by 2006 losing 220 million acre-feet per year. The models really haven't considered that at this depth, and that's right from NASA. I think we can zoom in here and take a look at what we're talking about in the Antarctic. Let me say it right. And it's that area right there. That's Pine Island and Thwaites. So you can burn that, jog that into your memory. So that's been in place for some 20 million years. It's melting and thinning at a record pace. If they collapse, just those pieces alone, the sea would in fact rise by 6 feet. Now, we're not saying it's going to collapse, but we should understand that it has a weak underbelly. That's what NASA is saying, and the British Antarctic Survey has said that Thwaites is in danger of imminent collapse. I don't know if that's 10 years, 5 years, but clearly scientists are absolutely concerned. There's no question. And behind that, the West Antarctic ice sheet, where Thwaites is holding that back, and if that collapsed, you'd see a sea rise of another 18 feet. We certainly hope that doesn't happen, but you can see these events being set in motion without question. You know, I like to go back in history and forget the models for a minute and just say, what happened in history? Did sea levels rise? Did they fall? How was that tied to CO2, and what really happened? Well, 3 million years ago, the sea was in fact higher, 75 feet higher than it is today. So 3 million years ago, 75 feet higher, and the CO2 was approximately 400 ppm, and the temps were only about 3 degrees warmer. So in fact, they were in some kind of cycle around where we were today, or where we are today. So 2008, we're just about at 400 ppm. So why were they 75 feet higher? Well, probably because it took several tens of years or hundreds of years to get there and have this feedback mechanism continue to rise the sea. We don't know how long that took, but we do know it was 75 feet higher and the CO2 was 400 ppm. 120,000 years ago, it was 20 feet higher than in 2008, and the CO2 was 300 ppm. Very interesting, right? And 20,000 years ago, 400 feet lower than 2008, and the CO2 was 200 ppm. So that gives you a range, and in fact, it gives us a range to just plot what happened in history, which I think is quite interesting to look at. And this is what historical sea rise looks like plotted across history, but more important, plotted across the CO2 ppm. And if we plot that against the actual ppm in the atmosphere that we're going, remember that earlier chart, best case, good case, status quo, this is what we see. We see over some period of time, and it may be hundreds of years, we see sea rises of over 200, approaching 300 feet. And that's tied to the the CO2 parts per million that we're putting in the atmosphere today. So this is tying actual historical data to the actual CO2 ppm that we see in the atmosphere today to the times that occurred in history. So I haven't seen this before, but I thought it was important to share with you what's going on. Now, obviously, there's a lot going on in South America that's a little bit scary. And in fact, a good part of the Amazon has been drying out, and and unfortunately burning. And that isn't just scary, that is actually a cause of CO2 and a cause of a feedback loop. And so, you know, when we change the Amazon rain patterns, we get some other things that happen. Warming shifts rain away from the Amazon. Multiple droughts start to take their toll on the trees and the other growth in the Amazon. Only 3 to 5 years of severe drought kills most trees. They just can't survive past that. So we really need to understand that that's critical. Trees store some 77 billion tons of CO2, and that's equivalent to 20 years of man-made CO2. And these are the trees just in the Amazon, of course. Trees die, the forest fires rage, CO2 is released, and it's already being released today. This is already happening today. So this is a problem. Obviously, that wasn't severely considered in our more conservative models. And let's jump to something else, right? So we're going right from the Amazon to permafrost. And permafrost can look like that. It can be that big. There's a picture of permafrost with a gentleman standing in front of it. And we have to consider permafrost because that stores methane in Siberia and other places of the world. It's already releasing some 50 million tons a year. That's equivalent to about 1 billion tons of CO2. And that, unfortunately, is rapidly accelerating since the average temperature in a lot of that permafrost region is now hovering around 32 degrees Fahrenheit. That entire region could be on the verge of collapsing, that permafrost melting and releasing that methane. If it all melted or rapidly collapsed, it would add 30 degrees Fahrenheit over some period of time to the average Earth temperature. That's about 500 billion tons of carbon. Don't even want to think about those scenarios, but this is just a fact. This is happening now. It's happening before our eyes. It's just one of the many things that we're seeing out there. And then we sort of have to look at our oceans. Our oceans are changing dramatically, certainly over the last 20 to 30 years. And a good portion of that is because it's been a CO2 sink. And it's been a CO2 sink for so long that it's really absorbed almost all it can. And that's a little bit scary. Since 1850, it's absorbed 130 billion tons of CO2 that have been made from humans, anthropogenic. And it's now more acidic. It's nearly maxed out on carbon. So, in fact, it may not be as much of a sink as it was at one time. And these changes can reduce the organisms, resulting in actual death in the ocean that we're seeing. We're seeing less fish. Obviously, some of that from fishing, but we're seeing a lot less organisms. We're also seeing shellfish that, because of the acidity of the ocean now, their shells aren't surviving. So it's a really serious issue. And as more of these things die, the ocean could, in fact, become a source of CO2 as they die because they're holding a lot of carbon themselves. So this is very, very scary. And we may have maxed out the ocean, and it was the ocean that sort of helped us all this time. And then we could dive deeper into the ocean and go to the bottom of the ocean. And at the bottom of the ocean, we've got things called methane clathrates. And in fact, 55 million years ago, we have some data that suggests that these methane clathrates, in fact, that are frozen at the ocean floor did break and come to the surface, and the methane was released. The ocean temperature worldwide only rose by a few degrees. But the clathrates shattered in less than 10 years, releasing at least 10 billion tons of methane just right into the atmosphere. Global temperatures rose some 18 degrees Fahrenheit very rapidly and caused mass extinctions. We know this happened from the fossil records, from the historical records, and from the ice records. So we know that this happened. We can see it. We're not including that in any models today, but it's something you should know about because it's underway. The ocean has warmed up, and it is more acidic. And then there's the extinction scenario, and I'm certainly not a proponent of suggesting this is going to happen, but we should talk about it. 225 million years ago was the end Permian era, and 95% of life on the planet perished. And the likely cause we thought was an asteroid, but now evidence suggests it was massive amounts of hydrogen sulfide. Now this is very early science, and it's quite controversial, but basically the oceans continue to lose oxygen because of acidity and because of the amount of CO2 that they've absorbed. You get reduced flow and further decomposition of organisms. Eventually, most of the ocean life dies. It rots and it's eaten by sulfur bacteria, and this sulfur bacteria releases hydrogen sulfide at levels that we actually can't deal with. It takes a very small amount in the atmosphere over long periods of time, some number like about 40 ppm, to basically kill virtually all life on Earth. So this is a catastrophic collapse. It is the extinction scenario. It is one of many extinction scenarios that are being floated out there, but this was an actual one that happened in history. It is suggested that volcanoes or other things released CO2 and raised ppm levels in the atmosphere. Because humans didn't do it, we weren't the cause a few hundred million years ago. Something else caused it, but the result was mass extinction. And we should just note that this is a historical, potentially a historical fact, and we should put that in our minds, right? So what's the projected temperature rise here? Well, if our projected temperature rise is 8 degrees, 10 degrees, 12 degrees, 15 degrees Fahrenheit over maybe 100 years or whatever the numbers are going to be as we approach 1,000 ppm, then is there a possible hydrogen sulfide feedback that begins? We don't know, because what we don't know is at what level of ppm, what level of CO2 in the atmosphere that this could happen. But clearly we have to note that it did happen over time, a long time ago. Like to look at worldwide sources of energy-based CO2. Industry responsible for 24%, some other transportation, airplanes and trains and things, 15%. But the three that are most interesting are the built environment, which includes building operations and building materials. Note that together they generate or are responsible for some 52% of CO2 in the atmosphere. 52% is tied to the built environment on a worldwide basis. Only 9% is cars. Important to note, only 9% is cars. So we talk about cars a lot. Of course, please go get a hybrid, get an electric vehicle if you can, but that's only 9% of the problem on a worldwide basis. 52% are the buildings we live in. And we're going to have to deal with that, and we're going to talk about that in another session that I give, but did want to point that out so that we can start thinking about our buildings and start thinking about some additional solutions. The Stern Review for the British government did assume some worst case scenarios. They said sea rise could be 15 to 20 feet in just a few decades. Florida, New York City, Monterey, California, London, Tokyo, all underwater, billion people displaced, floods, famine, disease, massive water and crop shortages worldwide, some $20 trillion or more in worldwide damages. Of course, if we mitigate now, total mitigation could be $1 trillion or less. So that's a Stern report for the British government. There will be wars over food and water. It's something to consider. It was a well-funded report, and we need to consider what was said there. The IPCC estimated costs are mitigate now would reduce GDP by about 0.6%, maybe as high as 3%, or do nothing, which even the IPCC would say is basically total economic collapse. This is from a great video on YouTube, and so I cannot take any credit for this, but I really love the concept. And the concept is, let's play a lottery. we can play the lottery of we act or we don't act, and there is climate change and there isn't climate change. So let's take a look at really the four possibilities of that lottery, because there's only four outcomes. So let's say that there is no climate change and we act. Well, we would waste money. We would invent new technologies, and we'd probably reduce our reliance on oil. So that's overall not a bad thing, but in fact, we did waste some money, and we need to note that. But if there is no climate change and we do not act, well, life goes on. So actually, that's not a bad outcome if you're playing the lottery. Now, let's say there is climate change and we do act. Well, we do spend money. We probably save 1 billion lives. We invent new technology, and we reduce our reliance on oil. That is actually a good thing, but we're going to spend some money because we had to act. Now let's suppose there is climate change and we choose not to act. We choose not to save any energy in our buildings, and we choose not to do anything with our cars or our industrial processes or anything else. Billions die, there's large war, there's horrible famine and drought, end of world as we know it, total economic collapse and possible extinction. Now, again, I'm taking this from a video on YouTube, but I just love the powerfulness of this message. There's really only one lottery ticket I would personally like to play, which is we act and we assume that there is going to be climate change. Because even if we act and there's no climate change, there's still some positive outcomes. But if we choose not to act, there's a chance, a 50% chance outcome in the we do not act category that awful things happen. So I personally am going to choose to act and continue to bring to market some world-class technologies that actually can address climate change, address CO2, and do everything we can now, as this says, right? Because there is good news. We can do an awful lot now. We can measure our carbon footprint, then reduce it, and we can address our built environment, which is the #1 issue. And that's the topic of another presentation as I said. So look, I want to acknowledge some people here and some books. The book With Speed and Violence, Why Scientists Fear Tipping Points in Climate Change by Fred Pierce is an outstanding book, and I do recommend that everybody here reads that. Climate Crash, Abrupt Climate Change and What It Means for Our Future, John Cox. Great book also. Want to thank some people at NASA for their help as well. So with that, thank you for your time. Please think about everything we do and everything you do in terms of using energy poorly, wasting energy, and generating CO2. And just do the right thing every day. Thanks a lot. Thanks for attending. Bye.